Good afternoon, everyone. Welcome to this third WorldCereal webinar. We're very excited to let you know about some new things, but let's give everyone a few minutes to join our meeting. If you, in the meantime, are facing any technical issues, you can send us a question using the Q&A button at the top. Okay, it's time to start. If someone joins later, not a problem. Our webinar is anyway recorded. Everyone who registered will receive a link afterwards to rewatch the recording or also share it with others. So on behalf of the European Space Agency and the entire WorldCereal team, I want to welcome you. Thank you for registering to this third webinar. So even though it's the third time already, we do have quite a few exciting things to share with you. And we do hope that you will learn quite some things from the different presentations that we'll have today. So in the meantime, just to let you know, the chat is disabled, but you should see a Q&A button on the top. If you have any questions, you can use the Q&A to ask your questions. You can also upvote others' questions or start a discussion. This is all moderated, so if you don't immediately see your question pop up, then you can be sure that we are evaluating that, maybe even already replying you with that. If there are any technical things, you can just use the same functionality, and then someone on the team here will try to help you out. So without further ado, the schedule for today is quite packed. That's why also today we have 1.5 hour of webinar. So I will be giving you a short overview of WorldCereal, not with too much repetition. We are very glad to refer to the previous webinars and many other resources we have that showcase the WorldCereal project. Most importantly are the three presentations that come after. So we have a presentation by a guest speaker, Gabriel Tseng from NASA Harvest, Mila, and AI2, who together with a colleague from the team, Christina Butsko, will dive a bit deeper in the scientific background of the new WorldCereal system and tell you a bit more about geospatial foundation models and how we actually deployed a foundation model called Presto within WorldCereal. Afterwards, my colleague Jeroen will take over the screen and will give you a demo in a Jupyter notebook on some exciting new functionalities that we can present today. most notably one of the most requested features, which is the ability to actually add your own reference data, which can even be private reference data, to augment the publicly available training data and create your specific custom crop type maps. Then afterwards, Lubos Kuchera from GSAT will take over and introduce you to a new other exciting functionality, which is the WorldCereal Processing Hub, which actually makes it much easier for the ones that don't like too much coding and Jupyter Hubs to run some default WorldCereal processes just from a user interface. And then finally, I will list some upcoming features still to expect in the future and conclude the presentations. Finally, we will have some Q&A, so hopefully by then we have a couple of good questions that we can address live. All the other questions will be taken up later on our forum. All right, so first things first, setting the scene. So what is WorldCereal? I hopefully shouldn't repeat that once again, but WorldCereal is an ESA-funded project starting with an R&D exercise, but now really going into an operational system. What's really important to realize is that WorldCereal is both a product but also a system. So there is the official WorldCereal products, currently still only for 2021. Another global production round is planned within the next few months. And WorldCereal is now also becoming really a system for everyone to use. So it allows you to produce your own WorldCereal products and do not depend only on the ones that are officially produced. We are nowadays talking mostly about that second part, the system, while we are getting ready for another global production round. So the WorldCereal ecosystem consists of 3 different tightly interconnected modules. The reference data module, which has been tackled already a while before, hosting both public reference data as well as private reference data. Then there is the visualization and dissemination module, which has a map viewer, a user interface, and now also a processing hub. And then under the hood, we have the processing module, which takes care of data fetching and pre-processing of satellite data, training or fetching of WorldCereal models, and finally also to run an inference and do post-processing to actually generate under the hood your crop type map. Today, we will give you a bit more scientific background on the models that are behind WorldCereal. Next, we will give you that demo where this new functionality now allows you to add private reference data into the WorldCereal models, and then also an overview of the new functionality launched today, which is the Processing Hub. So the reference data module, just very briefly, this has its own endpoint. You can reach it there, find all the reference data which is publicly available. You can also use it, and we highly encourage you to do so, to add your own reference data, which you can decide either to share with us for improving our models, share with the general public, or keep it all for yourself. We have a API access for easy interaction with all the data. We have AI-assisted private data upload, so that we automatically take care of translating your crop type labels into the harmonized crop type legend that we expect. And all of that is actually explained pretty well, if my slide moves on, into the MOOC that was recently launched. So if you haven't heard about the MOOC, you can find everything online or just scan the QR code. So this allows you at your own pace to learn about the reference data module and how to add data, which will be a prerequisite if you want to train WorldCereal models on your private reference data. Then the other module, the visualization and dissemination module, allows detailed and global exploration of the official products, but it also now has a processing hub, and Lubos will tell you a bit more about that. The hub itself can also directly be reached using this new subdomain of ESA WorldCereal, but also this will be explained in a little bit more detailed by Lubos later on. And then finally, the processing module is what is happening under the hood. This is a system that is fully implemented in the OpenEO processing language and runs by default on the Copernicus data space ecosystem. It takes care of getting access to the global Sentinel-1 and Sentinel-2 archives, the GOPDEM elevation model, and also the ACIRA-5 global reanalysis data of Meteo. Data loading is taken care of, pre-processing, and then finally we do a feature extraction and classification. And it's especially these parts, feature extraction and classification, that will be explained in a little bit more detail by Gabby and Christina. For the feature extraction model, we adopted the Presto model, which is designed by NASA Harvest. And this is why we are very happy today to have Gabby also giving a bit more insights into that. Nowadays, we have quite a few entry points into our ecosystem with different levels of accessibility and flexibility. So most accessible, but also least flexible, is that you just view and download the official products that I'm sure many of you are aware of already. Now we also have a very accessible and limited flexible default product generation method that runs in our processing hub. Lubos will tell you more about that. And then if you want to take it a step further, have some more flexibility, but it requires a little bit more of setup and diving into the code. We'll have, you can generate your custom products and even add your own private data. This requires, though, some experience to run at least through Jupyter Notebooks, although you can even just look at the source code yourself and implement your own workflows. All you need to get started is a CDSE account to actually run the jobs in the cloud. It comes with free processing credits, so you're free to try it out yourself. The code itself is on GitHub. This is also where you find direct links to the demo notebooks that Jeroen will be showing. It contains the entire system backbone, and then optionally, you can create a Terrascope account. It's actually a prerequisite to integrate your own data, because Terrascope is used for authentication of the reference data module. And also Terrascope allows you to actually run the notebooks that Jeroen will show without the need to install any environment. So if you want to go the easy way, a Terrascope account definitely helps. So finally, this is the link to our open source repository where you can find everything, also some links to some other resources. We have our forum. I'll show the link later on as well. You can use the GitHub to post any issues that you find. We're happy to help out. And also the links to the notebooks, like I mentioned, are there. With that, we're ready to dive into a bit more scientific detail. So I'm happy to introduce once again Gabriel Tseng from NASA Harvest, also a PhD student at Mila AI Institute and an intern at AI2. So we're very happy to have Gabby here today. After Gabby's general overview of the Geospatial Foundation models Presto, we'll have Christina from the team taking over to dive a bit into more detail on how we actually use the Geospatial Foundation models inside WorldCereal. So, Gabby, the floor is yours.
Thanks, Christoph. Hi, everyone. Let's see if I can change the slides. Okay, awesome. Yeah, so as Christoph said, I will briefly introduce Presto, the motivation for having a Geospatial Foundation model at all. So what is the motivation? Well, we would like to have a model that has a really good internal representation of the planet via remote sensing data, so that even if we have few labels, or more saliently in our case, very spatially or temporally imbalanced labels, the model will still do well. How do we do this? Well, we can achieve this by training the model on pixels from all over the planet, or on points from all over the planet. This means that we'd prefer not to need labels when we're training our model, because we don't want to be constrained to where we've collected labels. We want to be able to use places all over the globe when we're training the model. And so this means that we would like to train it in machine learning world. This means training in an unsupervised way. That just means training it without any labels. How do we achieve this? Well, here we can take motivation from other domains in machine learning where this question has really been investigated as well. And so this is what this image on the right shows. This is from the MAST autoencoder paper, which applies this principle of training a model without any labels to vision transformers using natural imagery. And the solution that was developed was to take an input and mask out or remove a whole bunch, randomly remove a whole bunch of the input. And so this is what these gray squares on the image on the left are. And then if you train your model to reconstruct what was removed, so you can see the image on the right has those gray squares filled in, it turns out you get a really powerful model that can then be applied for all sorts of downstream tasks. And so on the left, this is the Presto model, and we basically have taken this same idea, but applied it to remote sensing data. And so I'll spend a little bit of time talking about what modifications we made to make it applicable for remote sensing. I'm trying to change this. Oh, okay, great. So the first thing we do is use a wide variety of sensors at pre-training time. So one of the great things about remote sensing is that we can collect many different views of the planet for the same place in similar times, ranging from directly sensed things like optical or radar imagery, but also more processed inputs, things like weather or land cover maps or topography maps. We use all of these when we're training the model, and this lets the model learn relationships between these different inputs as well. However, at downstream time, or when we're applying it for a specific task, we might not have access to all of these inputs. For instance, there might be clouds that are making it hard to acquire optical imagery at a specific place. And so we basically anticipate this. Instead of randomly masking out bits of our input, we apply what we call structured masking, which tries to anticipate what this might look like at downstream time. At Harvest, we have a background in agriculture, and in agriculture, the temporal dimension is really important. And this means that we train Presto not on imagery, like with height and width, but we instead train it on pixel time series so that we can really emphasize the temporal dimension. And one of the other nice advantages of doing this is that we get a very small model. And so here we can compare to two other self-supervised models, and Presto is in green. And these, the size of the circles show the parameter counts. And so we're getting lots of bang for our buck in terms of performance for parameter. And finally, yes, the whole point of training in an unsupervised way is that we can sample from the whole globe. And this is something else we do. We specifically selected the training data for global representation as well as semantic diversity. I'll also quickly talk about like future steps for Presto, or how we at Harvest have continued iterating on the insights we had at Presto. And this is something we've recently put on archive. And this is a collaboration, as Christoph noted, with AI2 as well. And yes, you can find it at this archive link down here. I'll quickly talk about how we're improving on Presto. The first thing is that we're adding even more sensors. And so in addition to the directly sensed ones, we're adding things like the phase 1 WorldCereal map, and also things like TerraClim and Veer's nightlights. We've tailored the learning algorithms to make the most of unlabeled remote sensing data. So Presto was directly reconstructing the inputs, but other domains in machine learning, such as computer vision, have been thinking about how you can do better than these direct reconstructions. And we have also taken lessons from this. We've kind of kept the bang for the buck. So Presto remains, or this new version of the model, Galileo, remains very efficient while still performing well, especially compared to contemporary models. And finally, we have still sampled globally. So the main premise that it can be applied in many parts of the world at many different times, it still holds. We've still sampled the training data to try and make sure that this is the case. Yeah, and I'll pass over to you, Christina. Thank you.
Thank you very much, Gabi. I will now take control of the slides. And now, after this great introduction to foundation models, you guys must be as impressed as we were when we first heard about Presto. And if so, then I'm sure that you cannot wait to try it yourself and use all of this power of foundation models and Presto to your benefit. And if so, then no worries. I'm going to tell you exactly how to do that and how we did that. And even though Presto is a very powerful and flexible model, we still needed to adapt it to our WorldCereal needs. And that included additional self-supervised training. I need to change my slide. There we go. So yeah, one of the additional adaptations that we did to Presto was the additional self-supervised training step. so that we get Presto acquainted to the WorldCereal data with its own peculiarities, because the discrepancies in data are unavoidable, unfortunately, and we shouldn't aim for a line in all possible data sources, but we should have models that can accommodate that. And Presto does exactly that. We also introduced a rather clever concept of focus time token to help the model give more attention to time when crops and vegetation are in their prime growth phase, significantly improving results, especially in multi-season regions. Finally, we implemented temporal augmentations and different masking strategies at fine-tuning time, and refined class balancing as well. All of these to enhance models' robustness and reliability. We used these techniques to develop two parallel Presto-based models for two different tasks. The first one is binary cropland model. And think of this as your big picture model. It helps us identify agricultural land, separating temporary cropland from other land use types. The second model is multitask crop type model. This task is trickier, and it requires distinguishing between often subtle variations within agricultural land, allowing detailed crop type mapping. And this model operates within the temporary cropland only. Why two models? And this is a rather pragmatic decision for us. These two tasks are rather different in their scope and data availability, with significantly more labeled samples available for cropland task with much better geographic representation. Because as you see, only first part of the model training and adaptation is self-supervised mode, but then later we still need labels to fine-tune Presto. And in our experience as well, binary cropland classification is a very common and often demanded task on its own, so it deserves a separate model on its own. Although in future versions, we will add a cropland model that will cover, that we will allow custom definition of temporary cropland. Now, with these adaptations, we come to the power of Presto, to its embeddings. And let's talk about the embeddings themselves that we use as features into our downstream classifiers. And think of these embeddings as the dough for your classification pastry. While dough itself isn't a ready product yet, right? It needs still baking, flavoring, and shaping according to your unique preferences and availabilities. And similarly, Presto takes diverse remote sensing inputs, as Gabi mentioned, optical imagery, radar data, meteorological information, and topography, and transforms them into condensed and incredibly informative representations that are called embeddings. They contain rich and structured information about your data, capturing all the necessary characteristics in a compact and ready-to-use form. But the embeddings alone don't classify your crops. They provide a robust, versatile base, which can be quite easily adapted to your specific classification needs. Whether you are distinguishing maize from soybeans and cassava, or going for a challenging distinction among cereals, the final step, training a lightweight downstream classifier, is where Presto embeddings get truly customized. Now, what are the key decisions that you'll need to make when crafting your own customized classifications? And it's actually not too many. The key decisions that you'll need to make are basically choosing your classes, which means deciding exactly which crops you want to classify, and then choosing your season. This is identifying when your classes of interest are really there. Let's delve deeper into these decisions. Selecting the right classes is crucial. And while this part is will always be very, very case specific, here are some general recommendations that you can follow. Aim for at least 100 samples per class as a rule of thumb. Use hierarchical grouping to organize similar classes into broader and meaningful categories if sample counts are limited. Using the toy example on the slide, it's more meaningful to use more general fiber crops class than go for cotton and flax separately. And in general, we recommend you to be cautious about treating very similar classes separately. For example, wheat and triticale crops are very similar in their spatiotemporal signatures, making them very difficult to classify accurately. However, also feel free to experiment and apply your own expert judgment. Even if a particular crop like rapeseed in this store example, again, has fewer samples than the recommended threshold, it should be still sensible to keep it separable, to keep as a separate class, because rapeseed has a very distinct spectral signature. Remember that careful selection of classes sets your model for accurate and meaningful results. Now let's go to the next step, selecting the right season or window of interest. Why is this important? This concept of focus time that I mentioned before is a unique adaptation that we've made for Presto, guiding the model to focus specifically on the time of year when the crops are at their peak growth. While not really important in cropland tasks, this focus time makes a big difference in crop type classification, especially in places where 12-month time series data may contain multiple crop signatures. So by clearly defining your window of interest, you help Presto to concentrate on the relevant growth period. Now, here are some practical tips for selecting your season correctly. If you know quite confidently when your crops grow, position your window of interest, your season, in such a way that the middle of this window aligns roughly with the peak of the growing season. However, if you don't have a clue, you don't know this region where you need a map, then no worries. You can use WorldCereal crop calendars, which are also very readily available, and we will demonstrate that in the demo. And use that to help you figure out the optimal window for your region. And thus, this approach ensures that your model captures the clearest and most informative signals, maximizing the performance and reliability of the classification outcomes. Now let's look at the classification step itself. At this step, you will be able to train your own lightweight yet powerful downstream classifier. We've chosen CatBoost as our classifier of choice. CatBoost is short for categorical boosting, and it is a powerful open source gradient boosting library. While its key advantage is the ability to efficiently process categorical data without requiring manual encoding, it is also quite flexible, performant, and robust to overfitting. And we also had a very good experience with that in the previous stage of the project. So we already know this very well. There are several important components of CatBoost model training. One of them is class balancing. While it is usually recommended to use class balancing while you are training a multi-class classifier, and in our system, by default, class balancing is enabled to ensure fair representation so that your model doesn't overly favor common classes, it is sometimes helpful to try and make a run without it. Luckily, it is quite fast. Machine learning is indeed sometimes a lot like cooking, and certain lines in the recipe just may not work in your particular settings and just need to be adapted, removed, or replaced with something else. Another step is train and validation split and early stopping. This is a very common, I can even say a default mechanism to prevent overfitting. Once your data is prepared, the classifier will automatically and randomly split your data into two parts, stratified by classes, and then use the validation set to detect overfitting and stop the training before the model degrades in quality. And then optimization metrics. When we are training our classifier, we use the F1 score metric, as it represents a good balance between precision and recall, ensuring a well-rounded measure of performance. If you are a more advanced user, then you will be able to tweak these parameters yourself if you want. And if you are curious about more customization parameters, then you are very welcome to reach out to us, and we will be happy to assist you in further customization of your model. Now, like every truly amazing recipe always has this one secret ingredient that makes it like so good. Our system is also no exception. And for us, the real secret ingredient is local training data. And yes, it's that simple. Why is it so important, and how does it influence your model's performance? Integrating local data into your model significantly enhances its accuracy and relevance. Our experiments show that even small amounts can lead to substantial performance gains. For instance, adding just 50 samples per class can achieve nearly 30% of the potential possible improvement, while 500 samples can capture about 63% of the possible gain. However, the accuracy improvement plateaus at some point and expected gains get smaller. Still, with sufficient local samples, your model can perform on par with or even surpass existing state-of-the-art benchmarks. However, there is one important principle to remember here: quality over quantity. It is essential to prioritize clean and high-quality training data. Even small amounts of noise in training labels can degrade performance, with the impact becoming more pronounced as more data is added. Therefore, ensuring data quality is paramount, especially when working with larger datasets. So by adding your local data, you are customizing the Presto embeddings to reflect the unique characteristics of your region, leading to more accurate and reliable classification. This tailored approach ensures that your model is finely tuned to your specific agricultural context, resulting in insights that are both precise and actionable. Now, we'll show you how to actually transform your local data into these super powerful Presto embeddings, enrich them with available public data, and train your own classification models. Passing over to Jeroen.
Thank you, Christina, for the very engaging presentation. As mentioned, I will now give you a very practical demonstration of how we go about creating our custom crop type map for our region of interest. This scheme represents the basic steps that need to be taken whenever you want to engage in such an endeavor. So on the screen, you can see that we can start both from public and private reference data. For those, both of those sources, we need the respective Earth observation time series for all our observations. And that is something I will be showing you in the first notebook. I'll be demonstrating how to extract those EO time series for your private reference data. Then once we have all those required time series, we go into computing our Presto features, so our actual classification features. And then we are allowed to set some customization options, meaning that you can choose which crop types exactly you want to include in your model. And once you did that, we train a cut boost model, and we can use that model to generate the crop type map. So that's a bit of a quick overview of the steps that I'll walk you through. While I start sharing my screen, can I also remind you that whenever you have a question during my demonstration, you feel free to post it in the Q&A section of this Teams meeting. So let me share my screen. And you should be able to see the notebook right now. Okay, so we first start with our private reference data. So the idea is that you upload your data set. Imagine you have a nice data set with some point or polygon observations for your area of interest. We need you to upload that as a private data set to the WorldCereal reference data module. I included a link to a demo video on how to upload your data set in this notebook, so you can also always consult the procedure there. Maybe let's quickly go to this WorldCereal reference data module. If we hit there the Explore button and I quickly log in, yeah. Then we see the blue pins are all publicly available reference data. The red pins are my own private reference data sets, and I've been quite active. I've been uploading quite a bit of private data sets recently. So what we're going to do now is we're going to query this reference data module and see which private data sets are actually available. So if I run this first cell, I am required to authenticate. Yeah, I get a link that I need to click because I want to access my private collections. Authentication is always required. Seems it's a bit slow. Yeah. Okay, going back to the notebook. Authorization was successful, and you can see that I have in total 49 reference datasets, private ones. You can see the collection ID of every one of these datasets, and for each dataset I can request some metadata. Let's just pick the first one for this demo. And going to the next cell, I will download actually from the reference data module my full reference data set to the machine I am running this notebook on. So you can see that the samples for this collection have been downloaded to a download location. You can see here there's a download folder where I'm running this notebook, and my dataset was just downloaded there. Next, we prepare this dataset. What we typically do here is whenever your dataset contains polygons, we convert that to points using the centroid of the polygon. And we check how many, what the geospatial distribution of your dataset is. So here you see, for instance, that my dataset covers in total 51 Sentinel-2 tiles. So there's quite a big spread of my dataset, and this is how it looks like. So it's a harmonized dataset with harmonized attributes. You have for each observation a sample ID, a crop type label, and an observation date. Those are the most important features. When I execute the next cell, the extractions actually start. So what happens in the background is that first my dataset gets split up into multiple processing jobs. We split this dataset according to the Sentinel-2 grid. So you can see here my job data frame was created with in total 51 jobs that need to start running. These jobs are automatically submitted to the Copernicus Dataspace ecosystem using OpenEO, and they will start running and extracting the necessary EO time series. So as Christina already mentioned, we're extracting Sentinel-2, Sentinel-1, Meteo, and digital elevation data. This will take a while for this entire process to complete. So I will, for now, interrupt the processing here. But you get an idea of how it looks like. Once this processing is completely done, you can check what the status of your submitted jobs is. So here I used a previously done or completed data set to just show you what it looks like. So we first check the job status. We have 40 finished jobs and 1 still remaining in post-processing status. You also immediately get an idea of how many credits you consumed. So as Christophe mentioned, each CDSE user gets 10,000 credits, processing credits monthly. Here you can see, okay, I consumed in total 579 credits of those. I had in total 41 jobs for this data set, and on average, I consumed that much. You also get some details about the succeeded jobs, like the Sentinel-2 tile, the number of samples included in the job, and then again, this processing cost. Once you have all your extractions downloaded to this extractions folder, and I can also briefly show this, what it looks like. So here you will see this extractions folder, and there each data set gets a different subfolder. We can go into there. And then each individual job results in a, GeoParquet file, which contains all the extracted data for those samples. Afterwards, all these extractions are automatically merged into one single location, which is called WorldCereal Merged Extractions. And this is the folder that we will be needing in a future demo. Okay, what else you can do is you can load and inspect the extractions. So as you can see, we downloaded some Sentinel-2 data, and you can inspect the results like this. Or we have also some convenient function to, apologies, check the band statistics. I first need to do this, sorry. So for each sensor that was extracted, for each individual band, sorry, that was extracted, you see the percentage of no data in that band. You see the minimum, maximum, and mean and standard deviation values. So you can get a bit of a feeling of how your data looks like and whether it meets your requirements or your expectations. You also have the possibility to visualize some random time series in the extractions, and by default, this visualizes the NDVI for 5 random samples across the data set. But you can change all this behavior, like the number of samples to be shown, but also which band to visualize. These can also all be changed in this function, so you can really inspect your data set. Okay, so now we reach the end of this first part. So we have all the required data we need for our private data set to get started. So now we want to train our local custom crop type model based on our data. First thing, what we need to do is we gather and we prepare all the training data that we're going to use for the model. First thing I need to do is select a processing area, so an area for which I want to generate my map. Let's, for the purpose of this demo, zoom in, for instance, here on Mexico. People who have already seen other demos from the WorldCereal system might be familiar with this widget as well. So you can click this rectangle button here to start drawing a bounding box. And as soon as you drew it, it gets automatically saved, and you get a notification about the area of the extent you want to process. Then what we'll do in this next step is query our extractions. So query all the available reference data that we have, both public and private extractions in one go. For this, I need to provide the path to my private extractions, which I briefly showed you earlier. And upon executing this function, you will see that we apply a buffer to widen the search area in order to make sure that we find enough reference data. And then we get a summary of what we found. So for the public data, we found in total almost 2,000 samples, mainly coming from a USA data set, the USDA crop data layer in this case. And I also found 790 unique samples from my own private data coming from this one particular data set. You can also see again how the data looks like. This is the same that I showed you before. So each row in this data frame contains the extracted time series contains the extracted values for all the bands for one timestamp. Here you can again use the same functions as before to visualize band statistics and time series. In case you want to also inspect, for instance, the public extractions, you can freely do so here. Based on these time series, you can also already see, okay, when is the growing season happening in my area of interest or for my reference data points. And in this case, it seems the peak of the growing season is somewhere around January, February. Moving on, we will need to decide on which growing season we want to map. And if you don't have any clue about the growing seasons in your area of interest, you can always consult our WorldCereal crop calendars using this function. So this will retrieve our crop calendars for your area of interest. And you can see here that we have 2 seasons here, one starting October, ending in May, and one starting around June and ending in November. So also based on this information, you can pick your season of interest. Then in the next cell, we then need to specify our processing period. So maybe based on this scheme here, I can say, okay, I want to focus on this second season here. As Christina mentioned, we always require you to select a 12-month period, and you just need to make sure that the season of interest is nicely centered within this 12 months. So in this case, we make sure that September is rightly in the middle of our processing window, and you can double check that right here. Then we move on, and we prepare our training data to be used for the model. So I'll just run this for now. What will happen here is that any sample that you might have not matching your season of interest will be thrown out, just to make sure that we only train on relevant data which matches your season of interest. So here we actually have good news that no samples were removed due to this growing season selection. And we see a final overview. So we have 2,500 samples for the year 2019 and 200 for the year 2020. I will skip this one for now. So the next thing we need to do is we need to select the crop types of interest. So based on the contents of your training data, you will get an overview of which crop types are in there, and you can start selecting. For instance, you want to include wheat in there. I want to include maize. You also see for each crop type how many samples are in your data set. So based on that, you can also make a decision. So let's pick those. You get an overview of which crop types you selected. And if you execute the next cell, you can see how many many samples are available for each crop. Any crop type that you do not select here are automatically moved into this other temporary crops class. Finally, we prepare your data frame. We save it for future reference. Mexico test. I need to provide a name here. And this is how the final thing looks like, right? Wait. Okay, next, for each of our samples, we compute these Presto features that both Gabi and Christina have been talking about. So based on the extracted time series, we run this through the Presto model, and you nicely get these 128 Presto features for each individual observation. And you can see also here the crop type label for each sample. And this is basically the information that you need to start training your model, right? So for each sample, you have a crop type label and you have these Presto features. Those ones will then be joined together in this training routine. You can track the progress of the training. And then at the very end, a report is printed on the classification accuracy. So what happens in the background, as Christina already explained, your training data is split into a training and a test set. And using the independent test set, we get here these F1 scores for each crop type. So you can already judge how well your model would be performing. Next, we're almost there. In order to generate your crop type map, you will need to deploy your model in the cloud so that it's reachable from the Copernicus data space ecosystem. So we provide it with a unique name. It gets automatically uploaded to OpenEO, to the Copernicus data space ecosystem. And finally, maybe moving a bit faster now, we go into the actual inference. So this generate map function, what it will do, it will take your model and just apply it to the region of interest that you drew earlier, and to the apply it to the processing season or growing season that you selected earlier. I'm not going to launch this right now. This typically, depending on the size of the area you selected, this typically takes a while. So I had a pretty large processing job previously, and it ran more or less half an hour. You get a nice overview of which crop products have been generated. So you get a cropland mask. So where is cropland, where is no cropland, and then your customized crop type product. And at the very end of this notebook, you can then use this visualize classification function to have a quick overview of what your map looks like. Of course, all these results are also downloaded to your environment. So if we, sorry. For each run that you perform, you will get a series of TIFF files, which you can just load into QGIS. And here I, for instance, show an example again over Mexico, where you see clearly two distinctive regions, maybe one very much irrigated and one mainly rain-fed. And here our model clearly classified two different crop types on each side. So that concludes this full demo. So I've been through all the steps required for you to generate your custom crop type product. I will now give the floor to Lubos. Lubos will show you how to navigate through our new application, the Processing Hub. Go ahead, Lubos.
Thank you, Jaren. Hello, everyone. In the next 10 minutes, I will try to present you the quick introduction of the WorldCereal Processing Hub. Can you just skip to the next slide, please? Thanks. As already shortly introduced by Christoph, the WorldCereal Processing Hub is a new environment that provides the users user-friendly access to WorldCereal processing jobs. It allows launching the processing jobs, monitoring their statuses, and download the resulting maps. The Processing Hub has been developed as a standalone component of the visual and the dissemination module, and it can be accessed through the homepage of VDM. To work with the Processing Hub, the user needs to register at the Copernicus data space ecosystem, or it can use the existing account. In the current release, the Processing Hub supports two types of processes. The first one provides the access to existing global products and enable the downloading of selected products for user-defined area of interest. The other supported process aims at the generation of cropland mask, again for the user-defined area of interest, and it used the default WorldCereal cropland model. There's a specific tab in the application that provides the access to all the processes that has been created by the users. It allows the monitoring the status and downloading the resulting maps. And now I will switch to the short live demo of the application. Okay, so after the user logged into the processing hub, it is taken to the home page of the application, and it provides some basic description of the application, and also it includes links to some useful documentation or to other sites like CDSC or WorldCereal user forum. The other tab of the application guides the user through the downloading process. As already indicated in the current release, or so far only the collection of 2021 is available. So the product collection is defaulted to the year of 2021, and the user can select the type of the product that likes to download. In the second tab, the user can specify the area of interest for which the download will be run. In this, it's good to note at this stage that the main aim of this application is to allow the user to download the subset of the global products if the user is interested to work with large areas like continental products or global products, then it should use the links to other sites, like for example the Zenodo, which is and the link is put below the map window in this application. But to specify the area of interest, the user will use the map, and it can interactively select the bounding box defining the AI. In this application, the maximum size of the area is limited to 100,000 square kilometers, and this is also is integrated into the selection of the AI. So if the bounding box turns red, it means that the current area is above this area limit, but the user can resize the area to be compliant with the size limit. And after the box turns blue, then the user can continue to create the process. If the area is above the limit, then the user is not allowed to continue. Beside the specification of the output file, there is no other parameters to select, and so after the specification of AI, the user will create the process, and it could. And there are two options now. The user can directly launch the process, or it could go to the list of the processes just to check the parameters and to launch the process later according to his preferences. In this tab, the currently created process is visible on the top of this table. The user can check how the process has been parameterized and can launch the process. After the process finished, the status is changed, and the user will get the link to download the selected specified product, and also the description of the values that are used for coding of individual classes is added to this metadata panel. The third tab is provided to guide the users through the process of generation custom products. In the current implementation, the cropland product is supported, so the user can currently select only the cropland product. The classification model is currently defaulted to the generic WorldCereal model. In the future releases, the custom created classification model will also be supported. After selection of these parameters, again, the user will specify the area of interest. Here, the maximum area limit is decreased to 2,500 square kilometers. It's mainly due to the fact that the classification process that is triggered by this application is run on open infrastructure, and the user needs credits to launch this process. Some indication about how much credits will be spent for a concrete area, and also how long does the process takes are indicated below the map. Similarly to the download specification of AOI for product download, the user can specify the AOI for custom products. Again, the check for the maximum size is implemented, and if the area is below the maximum limit, then the user can proceed. In this case, there is another parameter to select. It is related to the selection of crop season. In the current implementation, the length of season is defaulted to 12 months. So the user will only select the ending months of its season of interest. And after that, again, the user can create the process, and it could be launched from the Your Processes tab. In this case, the processing of or the generation of custom products takes much longer, and after the process is finished, the user will get the download links to the resulting maps. In this case, two types of maps are provided to the user. The first one is represented by the raw classification results, and the other one with the post-processed extension in the name of the file. It includes the final map after the salt and pepper effects are filtered out, and some basic smoothing is applied. As it has been already presented by Christoph, the Processing Hub will be further implemented and further developed, and new functions and new tools will be developed. At the same time, we would appreciate also to get your feedback and your ideas on what you would like to have in this application. So feel free to share your opinions through the WorldCereal user forum, and we believe that during the next webinar we will present the updated version of this application. So that was all for the quick demo, and I am giving the word back to Christoph. Thank you.
Thank you, Lubos, for that overview of the new Processing Hub, which indeed supports now limited processes still, but it's something that will organically grow and also expose some more default product generation processes in the future, which are very convenient for anyone to run anywhere in the world without even the need to open a Jupyter notebook like the one that Jeroen has been showing. Okay, so as for the future updates that are still planned, and maybe first also taking a step back, for those of you who have been attending the previous webinar, you might see some of the text on this slide to be repeated from last time. This is deliberate because we still want to stress once again that some of these expectations still need to be managed today, just because we are working with satellite data to produce crop type maps, but also because the system keeps evolving. So the first one is definitely not something that we can resolve without your help, which is that a custom model, but also our default models, of course, can only be as good as the available training data that is there. There still is quite a lot of public training data that is in the stage of processing on our site to really expose it to you. But even when all of that is available, then still there are many big gaps around the planet that lack crucial data on crop types. Land cover is quite okay. We recently onboarded the Glance data set, which has an excellent global cover on land cover. But crop type, that's a different story. So if you now train your own custom model in a region where you have no private data available or only very limited private data, then don't expect a magic to happen. So your model will not be able to be top-notch if it cannot learn anything on what is happening on the ground. We do have default models. We're still working on the ones for the next standard official products to be generated. The current ones, especially for crop no crop, they aren't perfect. So like I mentioned, the glance dataset has been onboarded. Also, the world cover dataset is soon to be onboarded, but they are not all present in the default models yet. So also for this, we need an update. So for the time being, treat them with care. The default crop no crop classifier definitely has some imperfections here and there, and this is subject to updates in the near future. Once you launch jobs, Jeroen already mentioned that, it takes a while. 30 minutes, 40 minutes is not an exception. This means this is because a job runs from end to end. You launch it, and only then OpenAO starts extracting data from the Sentinel archive. All the data needs to be accessed, cloud masked, pre-processed, backscatter is computed on the fly on Sentinel-1. Presto is running over these pre-processed inputs. Then your CatBoost classifier runs, eventually returning you a geotiff. So all of that takes time. So be patient. This is just the reality. We don't have the local data available on your system. So that's just something that needs to happen. So that's fully natural. If you want to do large-scale processing over 2,500 square kilometer at once, currently, this is not meant to happen in one OpenAO job. So if that is the case, for the moment, we advise you to split up your extent in several smaller jobs and stitch the results together later. We also have some plans to automate this job splitting, but what always will be the case is that we won't have a single job producing a huge amount of square kilometers, because that just makes the system quite unstable. And also, if it then fails, then you need to start all over again. All right, then as for the next features, the current definition of cropland is still the official WorldCereal cropland definition. So that's the temporary crops. We have our own definition. So if you want to play with that, this is currently not possible. In a future update that's going to come soon, you will also be able to follow the same customization options of picking crop types, but then for the land covers, so that you can basically define your own cropland. If you want to include a specific land cover into crops, or let's say, for example, the permanent crops is something that for the moment doesn't fall under our cropland definition. That is something that you can play with soon. So that also, and that's then the next point, inclusion of permanent crop types will be supported, and then also your custom crop types can contain permanent crops as well. The processing hub is still in its initial stages. So like I mentioned, just a few default processes supported now. This will be expanded in the future. Definitely first up will be the default crop type processor, so that our officially supported crops can also be generated from the user interface. Then also briefly mentioned already, we have a lot of public reference data already available in the reference data module, but as Jeroen showed for your private data, these need to be extracted in the proper way. So with OpenAO, all these optical and radar extractions need to happen in the same way as we use them during inference, to make sure that we train a model in a reliable way. These extractions, they take quite a lot of time. The glance dataset is just something that we finished recently. It's not even crop type, but just land cover. This was a huge dataset that kept us busy for quite some time. This is now exposed to you, so you don't need to do those extractions yourself. You just can directly grab them from the S3 object storage. But for quite a few other datasets, parcel registrations in Europe, new USDA datasets that we want to interact with, Copernicus for GeoGlam datasets, many of those are available already as public datasets in the reference data module, but we don't have all the extracted EO data yet. And until that point, you cannot use those datasets to train your model. unless you would do the extractions yourself, which is not something that we necessarily advise because it can be a costly thing, and we are doing this anyway. Every time that we have a new data set fully ready, we will just add it to the S3 object storage, and your next query to the public extractions will automatically pick that up. So that's something that that will naturally evolve over time. Then there is the addition of the default crop type models. We only have a specific crop type model for the time being. We worked a lot on the user interfaces and things that happen under the hood. The models themselves with the new crop types for the next generation of global products is something that will follow later. So default other crops to be supported as part of the WorldCereal focus crops are going to be added later as well in the next few months. Then there will be an important addition of hierarchical crop classification. So as briefly shown already, we have now this crop type picker where you can choose your crops that you want to map. But in the end, the way we train the classifier is in a flat way. So whether it's wheat versus barley or wheat versus rapeseed, this is just treated at the same level by the classifier. We are quite close to a new version as well, where we will train CatBoost classifiers in a hierarchical fashion, which means that you can still regroup crops at a higher crop group if the accuracy in that case is better than going all the way detailed for each single crop. That's something that that will also be separately announced and that we will also communicate in more depth. Then onboarding of the service in the ESA network of resources. So you might be aware of the NOR initiative by ESA. This allows you to request funding, and if granted, you can have the processing cost covered by ESA. This requires the specific service for which you request funding to be onboarded as an official ESA network of resources service. For the time being, what is officially a service is the OpenEO on CDSE way of working. So you can actually already request resources, processing resources from OpenEO, which you can use to run WorldCereal products. But soon we also hope to have the ESA WorldCereal suite of services onboarded directly as well, which means that you don't have to go through all the processing hassle anymore, but you can just request the service to run the WorldCereal products for you. And then finally, we mentioned some small overviews on expected credit costs if you run jobs at the moment. This is still without quite some possibilities to work on the efficiency, though that's something that's also still coming up. We are working on compiling the PyTorch Presto model. We are working on increasing the efficiency of quite some other parts in the processing. So all of that will not increase, but further reduce the credit cost. So what a typical job costs now is something that we aim to reduce further in the future. So we are now at the, I wouldn't really call it worst case scenario because it's quite a good optimized system already, but this will still further improve in the future. Okay, and then finally, if you want to be part of our community, well, the fact that you are already with us here in the webinar means you did find us, so that's good. We have all these capacity building activities, of which the webinars are an important one. The first MOOC, as mentioned, was already launched as well. So keep an eye on our website, subscribe to our mailing list. We announce all our big events there, our participation to conferences, Living Planet Symposium coming up. We hope to have a very big presence there as well. Follow us on LinkedIn, rewatch all our recordings on our YouTube playlist. So there's many different ways to stay up to date on what happens and also to get in touch with us. Not here on the slide, but the WorldCereal forum, which you can actually consult from, for example, direct links on the GitHub repository or from the website, I think even, is the place where you can go for all kinds of questions regarding processing, regarding contents, whatever. Just engage with us and we'll provide you with an answer. Okay, this is it for now. That leaves us with 15 minutes to go over some of the questions that have been raised already. the two that I had written down already. First one by our GeoGlam director Sven Heliums with the question on when the new standard datasets will be available. I am assuming that these are the new global products that WorldCereal will generate. If not, Sven, then you can retype the question. But if this is the case, then the generation of these products will start in Q4 of this year. And this obviously will take a while. We also need to validate the products. So our current plan for release of the new global products will be around May 2026. So that still it takes quite a while. So we definitely encourage everyone to work with the system already, because the global products still will take a while, and even the exact processing year is still to be decided. Something that will be put in stone in June this year. So then we will know the processing year, and then expect it sometime May 2026. And then the other question that was raised already quite early in the webinar, and which I would like to pass to Christina, is the one on the ability to upload private reference data that may not coincide with the actual year to be processed. Christina, do you want to give an answer to this question?
Sure. The short answer to this question is no. Your reference data does not need to be from the same month, from the same year, I would say, because the concept of season that we are using is year agnostic. When you will be querying the public database to match samples with this season, we will be looking in for the same season across all the available years. However, having local training data, again, and by local, I mean not necessarily local in spatial context, but also in temporal context, never hurts. If you have data from the same year, that will make your model only better. So you don't need to have that for the same season that you want to make predictions on.
Okay. Thank you, Christina. Meanwhile, we also have confirmation from Sven that indeed the question was about the new WorldCereal products and which season. So yeah, the year is still to be decided. This is going to be either 2024 or 2025, and the seasons are the ones that will be covered by the new WorldCereal global crop calendars, which are actually not part of the current system yet. It just needs one update. These new global crop calendars are going to be closer to the reality in some regions where we have collaborated with local experts. And so these new seasons are now just covering 2 seasons in every single region in the world. So in the higher latitudes, this is the typical winter-summer season, while in the more equatorial areas, the 2 seasons are the 2 most dominant seasons that occur in each region. So this simplifies a bit the processing, also avoids some confusion on naming of seasons. So we have a season 1 and a season 2, and depending on how they were defined in the global new crop calendars, this is how the new global products will be generated.
All right, maybe moving on to the next question. We have a question from Charles on how does the model handle mixed crops? Maybe I can already very briefly comment on that at the moment we train our models based on pure crop types. So we do not include mixed crops as a class in our custom models. However, we are working on dedicated use cases together with our most dedicated stakeholders. And one of those is a use case in Malawi, where we want to demonstrate the applicability of the WorldCereal system to exactly monitor mixed cropping. In the case of Malawi, it's on maize and chickpea intercropping. So we really looking forward to work on that use case together with our partner there. And based on that, we might update the WorldCereal system to also explicitly be able to handle mixed crops. I'm not sure whether either Christina or Christoph wants to add anything to that.
Maybe I can add just a little bit that even though we do not fine-tune our Presto models explicitly for mixed cropping labels at the moment, you can anyway go ahead and try, because again, the Presto embeddings, they are 128 features that have a lot of knowledge and information there. If you have enough labels, it might still be possible to get somewhere. However, as Jeroen explained, we will be working on this dedicated use case as well. Yeah, it's a challenging case for sure, but nothing prevents you from trying it right now already.
Thank you, Christina. Then we have a question about credits. We couldn't go into a lot of detail today, so that's a good question. So how do credits work? Basically, when jobs are submitted to OpenEO, whether it's for extracting your private data or for running inference jobs, credits will be charged depending on the amount of CPU time that is needed to process your request. So everything that was actually shown from the notebook is something that happens on the Jupyter Hub service. If you use the Terrascope implementation, this is for free. So there is no compute involved when you train your models. If you deploy your models, that's not incurring any costs. It's only when you launch an inference job or an extraction job, so when you really send something to OpenEO that runs on CDSE, then this credit cost will be taken into account. So 1 credit is a little bit over 1 euro cent. So if we're talking about 100 credits, that's roughly 1 euro, a little bit more. If you register an account on CDSE, it currently comes with 10,000 free processing credits per month. So at the end of the month, this gets automatically reset. This means 10,000. This is a 100 euro processing cost that you get for free already, and we can assure you that you can do quite a few things with that already. Note though that this 10,000 is a temporarily elevated free credit amount that you get. If ESA at some point decides to remove that elevation, then we go back to the normal standard of 1,000 free credits per month. But even so, you should be good at doing quite a few WorldCereal jobs. It's also not the wall time, so if it takes 30-40 minutes, it's not necessarily going to take a lot of credits. It's really the CPU time that is used to automatically compute the credit cost. So yeah, I think it's documented in the notebooks and on the processing hub based on some tests what the average credit cost could be. Though we need to notify you that this is an average. If you are in, let's say, higher latitudes, then the satellite coverage is much higher, more overlap between the Sentinel-1 and Sentinel-2 SWATs. So the initial data that needs to be fetched from the archive to do the pre-processing just takes some more resources. So those jobs for the same kind of extent typically are a bit more expensive than the ones in more equatorial regions. But yeah, all of them are at the moment still at a fairly decent credit cost. And like I mentioned, if you run out, you can either purchase top-ups for CDSE credits, or you can engage with the ESA network of resources to ask for a sponsorship here.
Yeah, maybe just to give you a tangible idea for this demo, I created a crop type map in extent of around 200 square kilometers, and that cost me 60 cents. So just to give you a very rough idea, but for sure, indeed, these credits costs will most likely go down still in the future. In the meantime, we don't really see any new questions coming in. So please, if you still have a burning question, now is the time to put it in the Q&A. There was this very generic question from Fuad on basically how I understand this is how customizable the system really is. The answer, and I think we stressed it already many times throughout this webinar, we really want you to offer a fully customizable system, so you can indeed just input your own reference data that you gathered on the field yourself. If you want to have some guidelines on how to collect this reference data, also please make sure to check out our online course on reference data. There we provide some pointers to that. And then, yeah, I would say just try out the system and discover its endless possibilities, I would say.
In the meantime, we got another question on in-season crop type mapping, which is a very good one. Thank you for this one. So by design at the moment, I have a little bit of feedback here. By design, the system is currently end of season. So we look at 12 months of data and we expect the full season to be in there. Having said that, it is already possible for you, if you go into the customization options, to actually cheat somehow and just position your temporal slider in a way that your season is not fully included. But at the moment, the actual training still expects seasons to be kind of finalized. So we cannot guarantee that something very useful is coming out of that. Now, in-season crop type mapping, we learned that all the way at the start of WorldCereal is one of the biggest user requirements that we get, but it's just much more still at an R&D stage. Also because we want by design to be multi-year compatible and to train the system on 1 year and apply it to another, while with in-season, this becomes a little bit more difficult. Officially, it is not part of the plan of the WorldCereal ecosystem at the moment. Having said that, in the back end, with the Presto feature extractor and the downstream model, there is many possible ways to extend this, to actually cover exactly that use case. So there is no very concrete outlook on exposing this in a future update yet. We are fairly confident that one way or another, we will go into that direction and hopefully at some point also expose that. So for now, if you're happy to try out with some of the code, you can see already what it currently does for your situation, but we definitely plan to work under the hood in the future to also more explicitly do in-season crop type mapping. Okay. If there are no real other burning questions at the moment, then I suggest that we close for today. You will get a link, like mentioned already, to the recording afterwards. Also, yeah, by email. If you have any other kind of questions, engage on the forum, which is shown here. Yeah. Forum.isaworldcereal.org, or get in touch through one of our other channels. If no more questions in the meantime have come in, then I want to thank everyone for being here. Let's stay in touch. We welcome you as part of our community and stay tuned for further updates. Thank you also to the presenters. Bye, everyone. Till next time.